Hi everyone! Today we're going to continue our discussion on radioactivity. So how do we actually detect radioactivity? So for instance, if let's say you're working near a nuclear power plant or maybe you know that an area has had some radioactivity in the past. And how do you know if you're being exposed to radioactivity? Well, again, particles that are emitted by radioactive nuclei have a lot of energy, so they can be easily detected. Now, one option is something called a thermoluminescent dosimeter. So this contains crystals of salts, and those salts will, or at least the electrons in the salts, will get excited if exposed to high energy radiation. So remember, when electrons get excited, they jump to a higher energy orbital, and eventually they relax back down. And when electrons relax back down, they emit photons of light. So the light, or the amount of light that's emitted, is proportional to the radiation exposure. So sometimes these detectors will change color based on how much radiation you've been exposed to. And at a certain point, the color might get darker and darker, and eventually you'll know that you've probably been exposed to too much radiation and you should leave the area. Another way to detect radiation is using something called a Geiger counter or a Geiger-Müller counter. And one of those counters is shown off to the right. And it's kind of interesting because my high school was built during the Cold War, or kind of at the beginning of the Cold War. And I remember at one point they were kind of doing a cleanup of some of the basements in the high school. And it turned out that the high school had a bunker in it just in case Russia attacked America. And the bunker and some closets nearby had a Geiger counter so that they could detect radiation. So it was super old, but it's really cool because you'll notice there's this tube thing that they're holding, and that tube contains argon. So if a alpha particle or beta particle, let's say, enters the tube, it's going to ionize the argon. And remember, argon is a noble gas, so it would prefer to keep its electrons. But alpha particles and beta particles are so energetic that they can actually cause argon to lose an electron. So argon will become positive ions, and then the electrons that come off of those ions, they're detected by a detector or an anode in the little tube there. And what you end up hearing is a clicking sound. So every time an electron is detected, you hear a click, click, click. And that's how you know that you're detecting radioactive rays. So one other thing that is interesting with radioactive elements is that they have a half-life. So the rate of change in the amount of radioactivity is constant. So again, we might have some sort of rate constant, but that will be different for each radioactive isotope. So every isotope that is radioactive has a different half-life. So remember, a half-life means the time it takes for something to react or to decay. And each radionuclide, has a particular length of time that it requires to lose half of its radioactivity. So that's its half-life. Now, what's also great and this will make things a lot easier, is the half-life of a radioisotope follows first order kinetics. So we don't have to try to figure out if it's zero order or second order. It's all first order. All right, now unlike chemical reactions, the rate of radioactive decay or change is not affected by temperature, so that will remain constant, which is good. That makes things a lot simpler. All right, so in general, the rate of radioactive decay is equal to a rate constant, K, times the number of radioactive nuclei, N. Now remember, we said that this is a first order reaction or a first order decay. So the half-life of a radioisotope, T1/2, is equal to 0.693 over K. So this is something we learned about in chapter 14. So what this also tells us is that the shorter the half-life, the more nuclei decay every second. And we will say that the sample is hotter, quote unquote. Now, the shorter the half-life, the larger the rate constant. So for instance, some radionuclides or radioactive elements, they might decay a lot faster than other radioactive elements. Now, this might be a good thing or a bad thing depending on the situation. And we'll talk about some of those situations later on. So here's a list of some half-lives for different radioactive elements. So thorium-232 has a really long half-life. Its half-life is 1.4 times 10 to the 10th years. So it takes forever for thorium to go through its radioactive decay process. Now, as it does decay, it gives off alpha particles. And then uranium also has a really long half-life, at least uranium-238 does. Carbon-14, which we'll talk about later in more detail, that has a half-life of 5,715 years, and it goes through beta decay. So its half-life is a little shorter. Now, radon-220, that has a half-life of 55.6 seconds. Now, if you've ever bought a house or watched a relative or a friend buy a house, you might have heard of radon testing. This is something you can do during your inspection. And radon is usually present in rocky areas and like basements, etc. So that's something that inspectors should test for if you ask for it. And then, let's see, thorium-219. So this is a different isotope of thorium. This has a much smaller half-life than thorium-232. It's 1.05 times 10 to the negative 6th second. So that's a fraction of a second. So really, it just depends on the nuclide that you're looking at and what the half-life is. Typically, you'll be given the half-life, though, if there's a problem that you're solving for. Okay, so here is a graph showing the decay of radon-220. So let's say we start with 1 million atoms of radon-220. And the half-life of radon-220 is 1 minute. So let's say we wait a minute. We're going to hit 500,000 radon-220 atoms after a minute. And then after another minute, we'll reach 250,000 radon atoms. And after another minute, we'll lose another half of that, etc., etc., etc. So radon does decay fairly quickly, which again, can be good or bad, depending on the situation. Now, remember when we were discussing rates of reaction, we also talked about integrated rate laws. So down below is the integrated rate law for a first order process. And in particular, we've replaced the concentrations that we used to talk about with the number of radioactive elements that are present. So here we have the natural log of NT, which is the number of radioactive nuclei at a specific time point. And then that's over N0, which is the initial number of radioactive nuclei. And then that will equal negative of the rate constant times time. So that will be the time that we're considering for the decay process. So let's go over an example problem where we use that equation. So let's say that we have plutonium-236. So this is an alpha emitter. So it goes through alpha decay, and it has a half-life of 2.86 years. So let's write that down. Now, let's say a sample initially contains 1.35 milligrams of polonium-236. So N0 is equal to 1.35 milligrams. What mass of plutonium-236 is present after 5 years? Okay, so we don't know what N at time t is. So we'll leave that as a question mark. But we do know that the time we're considering is 5 years. Okay, so remember, we're going to use this equation, and I should put parentheses around that. Okay, so we have N0, we have time t, and we're trying to solve for NT. What we don't have is K. So we need to solve for that first. All right, so remember the half-life for a radioactive element is always first order. And this is our expression for the half-life of a first order reaction. So for this particular isotope, we know that that's equal to 2.86 years. So we can just rearrange that equation and solve for K. So K is equal to 0.693 over 2.86 years. All right. So if we plug that into our calculator, we get a value of 0.2423 per year. And that's our rate constant. So really what that's saying is we're losing 0.24 atoms per year. All right, so now we have everything we need to plug all these values into our equation below, our integrated rate law, and then we're going to solve for NT. Oops. All right, I went too far. All right, so I'm actually going to rearrange this equation to solve for NT. All right, so we're starting out with the natural log of NT over N0, and that's equal to negative KT. So let's take the inverse natural log on both sides. So we'll end up with NT over N0 is equal to e to the negative KT. And then all we have to do is multiply both sides by N0. And we have our expression for NT. So now we can plug in everything we know. So N0 is 1.35 milligrams. And then that's multiplied by e to the negative kt. So we'll put a negative sign, and then we just solved for k, so that's 0.2423 per year. And then t is 5 years. All right, and then all we have to do is plug that into our calculator. And you can do this in steps if you want. So for instance, you could multiply 0.2423 by 5, figure out what that is, and then take e to the negative of that value, and then multiply that whole thing by 1.35. And that might help you reduce errors that could occur. So remember, you can always go step by step. Okay, so what I got, and what the book got, was 0.402 milligrams. All right, so what that tells us is that after 5 years, our 1.35 milligram sample of plutonium-236 will decrease to 0.402 milligrams. Okay. Now, let's work on worksheet problem 5. So this has more of a medical application to it. So at 8 a.m., a patient receives a 1.5 microgram dose of iodine 133 to treat thyroid cancer. If the nuclide has a half-life of 8 days, what mass of the nuclide remains in the patient at 5 p.m. the next day? And we're going to assume no excretion of the nuclide from the body. Okay, so we're given a few different pieces of information here. So we're told that we have an initial dose or amount of iodine 133. So that's N0. And we're using the medical version of micro here, but you could also write this as the Greek symbol micro. Let's see, and then we're also told the half-life is 8 days. And then we're also told that the dose initially was given at 8 a.m. and we want to figure out how much is left at 5 p.m. the next day. So the total time, so we're going from 8 a.m. on day 1 to 5 p.m. on day 2. All right, and then we don't know how much is left. So NT is questionable. Okay, so maybe what we should do first is figure out how much time has actually passed from 8 a.m. to 5 p.m. the next day. So let's just kind of narrow down what that is. Okay, so if we're going from 8 a.m. on day 1 to 5 p.m. on day 2, we know that at least 24 hours has passed. And then how many hours would there be after that? So if we're assuming we're at 8 a.m. day 2, then 9, 10, 11, 12, 1, 2, 3, 4, 5. Okay, so I counted on my fingers. That was 9 hours. Okay, so if we add those two together, we get 33 total hours. Okay, so we're trying to figure out how much of this iodine 133 will be left in the patient after 33 hours. Okay, so maybe we're trying to make sure that we don't give them too much or too little. Maybe we want to make sure there's a certain amount over time. All right, now our half-life was given in years. So our half-life was, let's see, 8 days. Oh, sorry, days, not years. So maybe what we want to do is convert days to hours just so our units of time match up. So let's just do a quick conversion. So how many hours are in a day? 24. All right, so if we multiply that together, let's see, we get 192 hours. Okay. Now, remember, we're going to plug all of this information into the following equation. And similar to the previous problem we did, we weren't given our rate constant. So we need to solve for that. So let's actually solve for that. So similar to before, we know that the half-life is a first order process. So that's 0.693 over K. And we know that the half-life now is equal to 192 hours. So if we solve for K, that's equal to 0.693 over 192 hours. And let's see, so 0.693 divided by 192. That's going to give us a really small number. So we get 0.00361 for every hour. Okay, so we're losing a really small amount of iodine every hour. All right, so now it looks like we have everything we need. So let's plug this all into our equation. And I'm actually going to just use the equation we derived earlier, where NT is equal to N0 times e to the negative KT. Okay. So our initial dose was 1.5 micrograms. And we'll multiply that by e to the negative 0.00361 per hour times 33 hours. That's how long we were tracking the rate of decay. All right, so if we plug that into our calculator, what I got was 1.33 micrograms. So just double check my work there. I might have plugged something in wrong. It's been known to happen. Okay, so what this tells us is the patient will still have quite a bit of iodine left in their system after 33 hours. The dose didn't decrease by very much. Now, again, they might excrete some of this out, when they use the restroom, but it looks like a lot of this will be left. Okay. Now, earlier I mentioned that carbon-14 has a half-life of about 5,700 years. Now, we can use that to our advantage. And one way that we can use that is through what's called radiocarbon dating. So carbon-14 just naturally exists in the world around us. And all things that are alive or used to be alive contain carbon-14. So another way of thinking about that is all samples of carbon contain a small amount of carbon-14. And that amount of carbon-14 remains in our systems after we die. So for instance, it might be in our bones. And so we can actually use carbon-14 to kind of date how old something is. So again, carbon-14 is radioactive and it has a half-life of about 5,700 years. So the atmosphere actually produces carbon-14 at about the same rate that it decays. Down below, you'll see a picture of a very old piece of text, and these are the Dead Sea Scrolls. So these are 2,000-year-old biblical manuscripts, and their age was determined by radiocarbon dating. So this is a cartoon showing how carbon-14 kind of passes through different cycles of life. And I do really like seeing pictures of carbon-14 and how it works because it's hard to describe it. So basically we start out with nitrogen-14 in the atmosphere, and cosmic rays from the sun will collide with atoms in the upper atmosphere and produce energetic neutrons. And those neutrons will collide with nitrogen-14 and produce carbon-14 and a proton. So this is occurring naturally in our atmosphere. So now carbon-14 will oxidize to carbon-14 dioxide. So CO2, and the carbon in CO2 is carbon-14. So then CO2 will get transported to the lower atmosphere and is absorbed by plants during photosynthesis. So then, of course, animals and humans will eat plants that have carbon-14 in them. And then when plants and animals die, of course, they stop taking in carbon-14. They're no longer eating and ingesting carbon-14. So let's say we have a deceased animal. The animal has carbon-14 in its bones, for instance, and those will undergo beta decay to form nitrogen-14. Now, over time, the ratio of carbon-14 to other carbon atoms will decrease because carbon-14 is decaying, whereas other isotopes of carbon are stable, so they don't decay. So for instance, maybe if we're tracking the ratio of carbon-14 to carbon-12, that ratio decreases because carbon-14 is decreasing. So what we can do is use something like a Geiger counter, figure out how much radiation is coming off of an object, and then take the ratio of carbon-14 to carbon-12 and compare it to a fresh sample. And then what we can do is take the difference, do some math, and we'll figure out, okay, based on the half-life of carbon-14, how long ago did this object exist? So this is a really cool process. And it's really neat that scientists were able to come up with this process. All right, so just as a summary for radiocarbon dating, now while objects are still alive or around, the ratio of carbon-14 to carbon-12 is constant because the organism keeps replenishing its supply. However, once the organism dies, that carbon-14 to carbon-12 ratio decreases, and again, the half-life of carbon-14 is about 5,700 years. So again, we can use that ratio, compare it to a fresh ratio from a living organism, and then determine how old the object is. All right. Now, the limit for this technique is 50,000 years old, and that's about 9 half-lives. So after 9 half-lives, carbon-14 will be below the background radiation of carbon-14. So if we remember that decay plot from earlier, eventually we hit kind of a zero or approximately zero carbon-14. So it would be hard to detect it and then hard to even tell how old an object is. So there are other ways that we can date objects. So again, remember radiocarbon dating is limited to objects that are less than 50,000 years old. But what we can also use is uranium-238 and its ratio to lead-206. And this is a ratio that exists in what are called igneous rocks. So remember from our decay series that we talked about a while ago, uranium-238 goes through a bunch of different decay sequences, so alpha to beta to alpha to beta, etc., until it hits lead-206, which is stable. That whole process has a half-life of 4.5 times 10 to the 9th years. So it's a long process. It doesn't happen overnight. So what we can do is compare the amount of uranium-238 to lead-206 in volcanic rocks and meteorites. So the ratio would look like this. So for instance, how many stable lead isotopes have we created over time? So we're really looking at that ratio of like how much uranium is still left, how much stable lead have we formed. And so we can use that ratio similar to our radiocarbon dating ratio and figure out how old something is. So using this process, Earth's age is estimated to be between 4 and 4.5 billion years old. So that's really old. All right. Okay, so that being said, radiation, again, is really harmful to biological molecules. So, there's always some background level of radiation that's occurring naturally in the world around us. And it's not, that harmful because a lot of the time the half-life is really, really long. So our exposure to radiation is really low. But let's say that you live near a nuclear power plant or some area that has had a nuclear disaster, like 3 Mile Island or Chernobyl, then you might have more exposure to radiation. So 3 types of radiation effects that can occur are acute radiation damage, increased cancer risk, and genetic effects. So high levels of radiation over a short period of time can kill a really large number of cells. So that's not good, although we'll talk about later how we can use that to our advantage. So for instance, let's say that we're exposed to radiation after a nuclear bomb, or let's say we have an exposed reactor core at a nuclear plant or something. That's not good, right? So what that causes is a weakened immune system and a lower ability to absorb nutrients from food. And so if you have a weakened immune system, as we know with the current pandemic going on, you're more likely to become infected with potential viruses, for instance, and that could complicate things and result, unfortunately, in death. So the table below shows an approximate dose, and we'll talk about units in a bit. But you'll notice if you have a pretty low dose of radiation, you might have a decreased white blood cell count and a possible increase in cancer risk. But then as the dose increases, and this would be like over time, so if you had a consistent dose, you're going to find that you're getting sicker and sicker over time. All right. So again, low doses of radiation over an extended period of time do show an increased risk for the development of cancer. And what ends up happening is the radiation will damage your DNA, and that could kill some of your cells. And any changes in DNA can cause cells to grow abnormally, and so they become cancerous. And determining the exact amount of radiation that causes that is pretty difficult, but we just want to avoid radiation in general. So the damage that occurs in our cells could occur in reproductive cells with exposure to radiation, and that could lead to genetic defects in offspring, unfortunately. Now, this has been observed in animals, but not yet in humans. So from previous exposure to radiation that we've seen, though, that's pretty likely in humans. Okay, so let's talk about something slightly less depressing. We'll talk about units for radiation exposure. I guess it's still kind of depressing, but exposure is the number of decay events to which a person is exposed. And then a dose is the amount of energy actually absorbed by your body tissue. So one unit is actually named after Marie Curie, and it's called the Curie, and it's given the symbol Ci. So 1 Curie is equal to 3.7 times 10 to the 10th events per second. And this does not depend on the kind of radiation. Then there's also the gray, which is given the symbol GY, and that measures the amount of energy absorbed by body tissue from radiation. So 1 gray is equal to 1 joule of energy absorbed per kilogram of body tissue. And then the rad is a unit we use to measure the amount of energy absorbed by body tissue as well. So 1 rad is equal to 0.01 grays. So that's more of like a prefix almost, like we would use it to reference small amounts. Okay, so there is something called a correction factor, and this is used to account for different things that affect the result of exposure. So this is called a relative biological effectiveness, or RBE. And we use a unit called REMS. So REM stands for I can't pronounce this, Roentgen equivalent, man. So if we multiply a dose in rads by this RBE, or relative biological effectiveness factor, that will give us a dose in REMS. So again, this is just a corrective factor, almost like a standard deviation. You know, what's the amount of error here in our measurement? Okay, and we're not going to worry about units too much here, so I just wanted to kind of show you the different types of units for nuclear radiation if you're interested, but some of this is kind of tangential. All right, so what are some positive uses of radiation? We talked about some really depressing effects of radiation. Let's talk about some positives. So radioisotopes, or radioactive isotopes, can be used to diagnose patients. So actually, the author of your textbook wrote about how they went into the hospital because they had some pain in their lower abdomen, and they were worried it was appendicitis. And so what they did was they ingested a substance that is radioactive, and after about an hour, they scanned the patient's body. And if he did have appendicitis, the substance would have started attacking antibodies in near the appendix. However, they didn't see anything, they didn't detect anything, and so, he just left. But those are similar to what's called radiotracers. So radiotracers are radioactive nuclides that are attached to a compound. And they're used to track the we track the movement of the compound through the body. So this can tell us if there's a part of the body that isn't functioning correctly. And so that's detected via a Geiger counter or an X-ray or something similar. So off to the right is a bone scan. And here they use radio tracers to target the bones so that then they could scan the body and see where the radio tracer ended up. So there are different radio tracers we can use. Let's see. So iodine 131 can be used to study the thyroid. We can use iron 59 to study the blood. To study blood. We can use thallium 201, which uses electron capture to study the heart. And then fluorine 18 is used to study the heart and the brain. And then phosphorus 32 is used to study tumors. So we can then detect tumors in a patient. So I mentioned a PET scan, well, sort of, on the last slide. So a PET scan stands for positron emission tomography. So this isn't, what you use to scan your PET. So positron emission occurs for F18, fluorine 18. So if you ingest glucose that's mixed with fluorine 18, then the fluorine 18 is going to emit positrons, and you can scan the brain to see if it detects any of the positrons that are emitted. And so this can be used for various diagnoses, but you might know somebody who's had a PET scan before. And that's how it works. And then radiotherapy can be used to kill cancer cells. So cancer cells are more sensitive to radiation than healthy cells, which is a good thing. So radiation therapy can be used to kill cancer cells without doing significant damage to the body. Now, of course, there are side effects for all of these things. You do have to be careful about the dose or the amount of exposure because, again, radiation can cause harm, but we can utilize radiation in healthy, positive ways, even though it is very destructive. All right, so next time, our last lecture, we're going to talk about fission and fusion and nuclear reactors. So if you're interested in that, definitely tune in to the next video. If you're not interested, I'm not really going to test you on it, so don't worry about it. But I do encourage you to watch the next video. All right, so I will see you then.